We live in exciting times where robotic research algorithms are finally starting to make their way en masse onto commercial robotic platforms, especially in the service robotics industry. This presentation is about new research enabling these platforms to operate under a wider range of conditions with the cheapest possible visual sensing hardware. Two of the most successful application areas of domestic service robots are indoor robotic vacuum cleaning and outdoor lawn maintenance. However, most current technology is fundamentally limited in one or more commercially sensitive ways. They either only operate under ideal daylight conditions, or require the use of human-placed artificial beacons, or require onboard active sensing and/or lighting. These limitations affect the customer experience both in terms of the effort of setting up an environment for the robot and also with regards to the intrusiveness of the robot in that environment. Ideally, we would like our service robots to function under any possible environmental conditions, such as in the middle of the night when we're not using the environment. Through new service robots like the Dyson 360i robot vacuum cleaner and the Neato robot vacuum cleaner, we are starting to see the development of specialized, mass-produced sensors. For this research, we used two standard consumer camera setups, a panoramic camera from Ricoh and a consumer camera attached to a 360-degree optic. These sensors are massively overspecified in terms of resolution and quality for the end application, but provide a means of testing the algorithms developed in this work. The research presented here builds on the foundation provided by the SequenceLAM algorithm, a sequence-based place recognition algorithm that works particularly well in changing adverse environmental conditions. The original SequenceLAM algorithm works well on route-like environments such as road networks and indoor office environments. We expanded the SequenceLAM algorithm from operating in one dimension along route-like environments to operating in open field environments such as the interior of a house or a garden lawn. This slide shows the imaging setup for the indoor and outdoor environments and shows examples of the imagery produced by the sensors during daytime and nighttime conditions. There is a significant degree of perceptual change, especially in the outdoor environment. This slide shows an example of the localization results achieved using a single image-based method, shown on the left of the slide, and a sequence-based method, shown on the right. You are looking at a heat map visualizing the layout of an indoor lounge room from above for a particular localization query based on the current nighttime camera image. The size of the green circles indicate how strongly the current camera image matches to reference daytime images obtained at various locations throughout the lounge room. On the left side of the slide, you can see that the single image-based estimate of the camera location, shown by the black cross, is incorrectly not at the correct location, shown by the red plus sign. On the right side of the slide, you can see that the sequence-based location estimate is correctly co-located with the ground truth location. Neither of these environments was truly dark, so we performed additional experiments investigating the potential for new conventional low-light camera hardware, in this case a Sony A7S camera, to perform place recognition in very dark conditions. Walking along a wilderness reserve with almost no ambient lighting, the approach was able to achieve near-perfect place recognition performance, performing most strongly in parts of the environment where there was no lighting at all. Although this camera technology is currently relatively expensive, it will continue to reduce in price. It also has a 12 megapixel capability, whereas the algorithms presented here only need about 1,000 pixels, raising the possibility of mass-produced, low-resolution sensors for future service robot generations. This presentation has provided a brief overview of research being performed to enable service robots to localize and navigate under challenging environmental conditions using the cheapest visual hardware possible. For more details on the approach, future work, or for general inquiries, please refer to the paper or get in touch with us.